Hey, this is Aditya. Welcome back to another math video. In this video, we are going to look at the problem in International Math Olympiad 2021. Let's check out the problem. This is the first problem in IMO 2021. Pretty interesting, a tricky one. And the problem is let n is greater than or equal 100 be an integer. Ivan writes the numbers n plus 1 up to twice n, each on different cards. He then shuffles these n plus 1 cards and divides them into two piles. Now we need to prove that at least one of the piles contains two cards such that the sum of their numbers is a perfect square. Let's understand the problem step by step. Suppose these are the cards numbered on them, n plus 1, n plus 2 up to twice it, and Ivan writes the numbers on its cards, and there are total n plus 1 cards, and n is greater than or equal 100, which is an integer. He then shuffles these n plus 1 cards and divides them into two piles. We suppose take this as cardstock A and the cardstock B, and we need to prove that at least one of the cardstocks contains two cards such that the sum of their numbers is a perfect square. This is the problem, and hope you understand the problem. You might have an idea about the problem, and let's move towards the solution. Here we go. Let us assume that there exist three cards such that every pair of them sum to a perfect square, and then we can assume that one of the cardstocks contain two cards that the sum to a perfect square. Let a perfect square be x square, y square, and z square, and u, v, w are the numbers on three of the cards. Therefore, u plus v equals x square, that is a perfect square, and v plus w is equal y square, and u plus w is equal z square. And after solving this equation for the value of u, v, and w, we get 2 of u plus v plus w is equal x square plus y square plus z square. Now we can find the value of u plus v plus w, that is u plus v plus w is equal x square plus y square plus z square divided by 2. And we can find also the value of u, v, and w. For that, from this expression, we can put the value for u plus v, that is x square, and we get the value for w, that is w is equal x square plus y square plus z square divided by 2 minus x square, which gives a value of w, that is equal y square plus z square minus x square divided by 2. And similarly, we can get a value for u and v also. Therefore, we write the numbers: u is equal this one, v is equal this one, w is equal this one. That is u is equal x square plus z square minus y square divided by 2, v is equal x square plus y square minus z square divided by 2, and w is equal y square plus z square minus x square divided by 2. Now put a value for x square, y square, and z square is equal 2k minus 1 whole square, 2k whole square, and 2k plus 1 whole square respectively. We get, and putting the values of x square, y square, and z square in the u, v, and w, that is the equations, we get u is equal 2k minus 1 whole square plus 2k plus 1 whole square minus 2k whole square, which for which the value of u is equal this one. And after solving, we get the value for u, that is u is equal to 2k square plus 1, and we can get a value for v and w in a similar fashion, that is v is equal to k into k minus 2, w is equal to k into k plus 2. Now we have to prove that there exist three numbers in these forms between n and twice n, for which n is greater than or equal 100, where v is the least of them, and w is the greatest of all three numbers. It is sufficient to prove that there exist numbers in the form of 2k into k minus 1, 2k into k minus 1, and 2k into k plus 2 between n and twice n. And for these two numbers in the form of 2k into k minus 2 and 2k into k plus 2 to be in between n and twice n must satisfy inequalities. The inequalities is 2k into k minus 2 is greater than or equal n, and 2k into k plus 2 is less than or equal twice n. Since the 2k into k minus 2 is a least number, and 2k into k plus 2 is the greatest of the three numbers, therefore these two values lies between n and twice n. Therefore, after solving the inequalities, we get k is greater than or equal n into n, k is greater than or equal under root n by 2 plus 1 plus 1. And similarly, if we solve these inequalities, we get the value k is less than or equal under root n plus 1 minus 1. And k must be an integer because of the values, and therefore there must be an integer between under root n and n plus 1 minus 1 and under root n by 2 plus 1 plus 1. When these two differ by at least 1, therefore under root n plus 1 minus 1 minus under root n by 2 plus 1 plus 1 is greater than or equal 0. That is, if it is differ by 1, then we can guarantee that there is an integer between them. After solving this one, under root n plus 1 minus under root n by 2 plus 1 minus 2 is greater than or equals 1. After solving the inequality for the values of n gives n belongs to 107 and infinity, which is a half of an interval. And if we test manually from 100 to 106, we can show that there is an integer between under root n minus 1 and under root n by 2 plus 1 plus 1, for which n is greater than or equal 100. Therefore, there exists a triplet of integers, that is u, v and w, with u, v, w belongs to n plus 1 up to twice n, for which n is greater than or equal 100, such that every pair of numbers sum to a perfect square. By the pigeonhole principle, we know that two of the numbers must be on the cards in the same pile. Hence, we can conclude that when n is greater than or equal 100, there will always be a pile with two numbers that sum to a perfect square. This is the proof. Hope you understand the solution. Thanks for watching. Please like, share and comment. Thank you. Have a great day.